I'm Dr. Chris Masterjohn of chrismasterjohnphd.com, and I'm here with Alex Leaf of examine.com. You're listening to episode 60 of Mastering Nutrition, where we talk about niacin, part 1, what it is and why you need it.
This is Mastering Nutrition with Chris Masterjohn. Take control of your health, master the science, and apply it like a pro. Are you ready?
Niacin, niacinamide, nicotinamide, nicotinamide riboside, nicotinamide mononucleotide. Oh my. We are continuing our series on managing nutritional status. And once again, as per usual, I'm here with Alex Leaf. Alex holds a master's degree in nutrition from Bastyr University. He's a primary researcher at examine.com and part of the teaching staff at University of Western States for their Human Nutrition and Functional Medicine program. And he has a website, alexleaf.com. In this podcast today, we are starting off telling the stories of John, Jane, and Julie. John's taking a drug to manage his blood lipids and winds up with liver failure. Julie's trying to eat right, trying to eat healthy. She winds up with depression and eventually is diagnosed with schizophrenia. Jane is taking a darling anti-aging supplement and she winds up with seesawing energy and seesawing mood and emotional health. We then relate these stories to niacin. We talk about niacin in its classical deficiency, Pellagra, but then we talk about what it might mean to have suboptimal niacin status now that Pellagra is mostly, but not entirely, a thing of the past. We talk about what niacin is and what it does in the body. We compare and contrast its role in energy metabolism with riboflavin, and we see why it's so much more universal, and it doesn't have the impact that riboflavin has on burning carbs versus fat and needing more for one or the other. We talk about the difference between NAD and NADPH in metabolism, how NAD helps us break down food for energy, and how NADPH helps us recycle nutrients like folate and vitamin K, helps us with antioxidant defense and detoxification, helps us synthesize things, build them up, like cholesterol and neurotransmitters. We talk about the mechanisms of the niacin flush and what, if anything, you can do to prevent it if you're using niacin to manage your blood lipids. We talk about the mechanism of niacin-induced liver failure and what you can do to prevent that, if anything. We show how the biochemistry of how niacin works in the body explains the dermatitis, diarrhea, and dementia, a term that can range from simple depression to schizophrenia-like psychosis. How the biochemistry of niacin explains all of these features of niacin deficiency. We cover the role of NAD in longevity, anti-aging, DNA repair, lengthening telomeres. Why health-promoting activities like getting sunlight or avoiding refined grains can hurt your niacin status. And finally, we talk about how we get niacin through multiple ways, why it's different when we get it from animal foods versus plant foods versus synthesizing it ourselves from protein. How it's absorbed and transported in the body and why it would make any difference whether you take nicotinic acid or niacinamide / aka nicotinamide, or nicotinamide riboside, or nicotinamide mononucleotide, or NMN. Or what happens when you inject NAD, all from the basic physiology to the look at what studies show the supplements do in humans. As per usual, I focus on the basic science involved, and Alex focuses on what happens when you take supplements. This is part 1 of a 2-part series. Part 2 will be published in 2 weeks from now and will be on blood tests for managing niacin status, niacin from foods, and niacin from supplements. How we should eat to nourish our niacin status, and what we should expect for health effects when we take niacin supplements. If you want both parts right now, if you want transcripts and you want no ads, you can sign up for the CMJ Masterpass at chrismasterjohnphd.com/masterpass/mastering nutrition. If you use that URL or you click the link in the description of this episode, that will give you a 10% lifetime discount on the program. Without further ado, let's hop right into all the details right after this word from my sponsors. This episode is brought to you by Ancestral Supplements. Traditional peoples, Native Americans, and early ancestral healers believed that eating the organs from a healthy animal would strengthen and support the health of the corresponding organ of the individual. For example, the traditional way of treating a person with a weak heart was to feed the person the heart of a healthy animal. Modern science makes sense of this. Heart is uniquely rich in coenzyme Q10, which supports heart health. The importance of eating organs, though, is much broader than simply matching the organ you eat to the organ you want to nourish. For example, natives of the Arctic had very limited access to plant foods and got their vitamin C from adrenal glands. And vitamin C is important to far more parts of your body than simply your adrenals. In his epic work, Nutrition and Physical Degeneration, Weston Price recorded a story of natives who cured blindness using eyeballs, which are very rich in vitamin A. But now that we understand vitamin A, we know that we can get even more vitamin A by eating liver, making liver good for your eyes. Our ancestors made liberal use of organ meats both to be economical and to utilize their healing and nourishing properties. Animals in the wild do the same. Weston Price had also recorded a story of how the zoos in his era were capturing lions, tigers, and leopards, oh my, only to watch them become infertile in captivity. Researchers then observed what the lions did when they killed zebras in the wild. What they did was they went straight for the organs and bone marrow, leaving the muscle meat behind for the birds. But even the birds took what they could of the organs and bone marrow. Price reported that once the zookeepers started feeding the animals organ meats, boom, their fertility returned. The problem I often encounter, though, is that many people just don't like eating organ meats. Let's face it, if you weren't raised on them, it can be very hard to acquire a taste for them. That is where Ancestral comes in. Ancestral Supplements has a nose-to-tail product line of grass-fed liver, organ meats, living collagen, bone marrow, and more, all in the convenience of a gelatin capsule. For more information or to buy any of their products, go to ancestralsupplements.com. Ancestral Supplements, putting back in what the modern world has left out. This episode is brought to you by Ample. Ample is incredible. It's a meal in a bottle that takes a total of 2 minutes to prepare, consume, and clean up. 2 minutes. I'm not kidding. Now, I know what you're thinking. Anything that quick just has to be made of synthetic ingredients that you'd have a hard time pronouncing and wouldn't want to put into your body. But it's not. Ample is made entirely from natural ingredients and designed to provide an optimal balance between protein, fat, and carbs, as well as all the vitamins and minerals that you'd need in a single meal. There's no question that it's always best to sit down and take your time eating a home-cooked meal from fresh ingredients. But let's face it, oftentimes we just don't have time for that. If you live a busy life like I do and your goal is to get things done, you need quality fuel that you can get into your system quickly. Here's a great example where Ample is perfect for me. When I shoot videos, it takes hours to set up and break down all of my equipment. So I try to get as many videos shot in a day as possible. This prevents wasting a lot of time on setup and helps me conserve big blocks of time outside of shooting videos to get into a flow state where I can research something to my heart's content and spend all the time I need thinking about it creatively and analytically. But if I spend hours dealing with recording equipment plus hours spent preparing food, eating it, and cleaning up, there's no time left over to actually shoot any videos. So on recording days, I use Ample to maximize efficiency and focus on getting things done. Ample comes in 3 versions: original, keto, and vegan. And each version comes in 2 portion sizes: 400 calorie and 600 calorie. The 600 calorie original version gives me 37 grams of protein from a mix of grass-fed whey and collagen, which promotes satiety and flips my brain on. Its fat comes from coconut oil and macadamia nut oil. I like these oils because they're low in polyunsaturated fatty acids, or PUFAs, oils that promote aging and are usually loaded into the processed foods that most people eat when they need something on the go. The coconut oil provides some medium-chain fats to keep my energy levels up, too. The carbs, the vitamins, and the minerals all come exclusively from food sources like sweet potatoes, bananas, cocoa powder, wheat and barley grass, and chlorella. It's full of natural prebiotic fibers and probiotics to promote a healthy microbiome, and the gentle sweetness comes from a mix of honey, monk fruit, and stevia. I just mix it with water, drink it, rinse out the bottle, and boom. 2 minutes in, and I'm fully fueled and ready to face the next phase of the day. I first came across Ample when I met its founder and CEO, Connor Young, at PaleoFX a few years ago. Connor inspired me with his vision for Ample, which I anticipate will be much more than a meal in a bottle in the near future. I've become an official advisor to Ample, and I'll be helping Ample design scientific research that will lead both to an ever-improving Ample and, I hope, meaningful contributions to our understanding of how to use nutrition to help people be healthier and happier and perform better at the challenges that they care most about. As a listener to the Mastering Nutrition podcast, I've also worked out a special deal for you. If you use the discount code CHRIS15, you'll get 15% off your first order of Ample. To get your discount, go to amplemeal.com. That's amplemeal.com, 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 and use the code CHRIS15 at checkout. Let's begin our trek into our discussion of niacin with the stories of three people, Julie, John, and Jane. Julie is a vegetarian. She subsists primarily on whole grains at first, but she develops gastrointestinal problems. She reads about phytate in whole grains. She reads about iron and synthetic vitamins in the refined grains, and she seeks out something that's much more natural. And that is refined grains that have been specially produced not to be enriched with the synthetic vitamins and the iron in the inorganic form that she knows from experience and has read causes gastrointestinal symptoms, the exact thing that she's trying to avoid. After a while, she starts to get depressed. It's wintertime, and so she thinks maybe it's seasonal affective disorder. She Googles it, she reads online, she talks to some knowledgeable friends, and it all makes sense. And so she starts going out of her way to experience sunlight. Even though it's cold, she goes outside. She starts tanning beds, she starts some light therapy, but when she does this, over time, she starts to develop some skin problems. In particular, the backs of her hands start to get red. And it just doesn't look good. It makes her a little bit more depressed. Why bother getting your nails done when the back of your hands look all red and inflamed? And so she says, all right, I can't deal with most of this light exposure. It seems to be making everything worse, so I'm going to switch just to using light therapy on my eyes. And as she does that, the skin problems start to go away. But the light therapy does nothing for the depression. So she goes to see a psychiatrist. The psychiatrist puts her on an SSRI, a serotonin reuptake inhibitor, an antidepressant. But that doesn't help. She just progresses worse in the depression. Eventually, she becomes suicidal. As things get worse, she experiences auditory and visual hallucinations. Eventually, she's diagnosed with schizophrenia. We'll come back to Julie later, but now let's consider the story of John. John has diabetes. He has a history of non-alcoholic fatty liver disease. His triglycerides are high and his cholesterol is high, as you would expect from someone who has diabetes and non-alcoholic fatty liver disease. He goes to the doctor, and the doctor puts him on nicotinic acid to lower his blood levels, his blood lipids. Nicotinic acid is a form of niacin. He's first on the immediate release nicotinic acid, and he develops the typical flushing response. His face turns red. He's itchy all over. So the doc puts him on slow release nicotinic acid, and those flushing responses go away, but his cholesterol and triglycerides are still too high. He's on 500 milligrams at first, but then increases the dose, and then increases the dose, and then increases the dose. The flushing response doesn't come back, and eventually he gets up to 3 grams, where it seems to be having a good enough effect on his blood lipids. But at this dose, he gets nausea, he gets headache. Eventually, his skin starts turning yellow and he has jaundice. And eventually, he's admitted to the hospital for liver failure. Okay, enough of John. We'll come back to him. Now let's consider our third and final story of Jane. Jane is kind of low in energy and wants more. She is very interested in the anti-aging scene. And so she decides that she wants to take the new darling of the anti-aging industry, Niacin, or nicotinamide riboside. At first, she takes it at the recommended dose, planning to go on it for about 6 weeks. And the first 2 weeks, she did 3 workouts, up from her usually 1 a week would crash her. Now she's up to 3 workouts and she feels great. She feels like she's got still more energy in the tank, and she wasn't sleeping as much, but she just felt so high on life that she didn't need this sleep and just bouncing full of energy. But by week 3, things started to change a little bit. So mentally, she had a little bit more clarity still, but now her energy and her workouts is starting to tank. And then the next week, she starts getting emotionally messed up. She starts feeling depressed, emotionally suppressed, angry, just generally feeling bad. So she stops taking the Niacin for a few days, and then her energy goes down even further. So she gets scared and adds it back. But again, the energy comes back a little bit, but she just feels completely tanked emotionally and psychologically. Thoughts and feelings are getting stuck in her head. Like if they pass through her mind, they stay there, no matter how bad they are. Usually if a negative thought comes through, she can get rid of it. But now if the negative thought comes through and she wants to just ignore it, it just plants itself in her brain and she ruminates on it. All right, so in these stories, what do John, Jane, and Julie have in common? Well, they all have some kind of negative response to too much or too little niacin. And to understand exactly what's going on in these stories, some of which are real, some of which are fake, and I'll explain later, let's start talking about what niacin deficiency and toxicity look like. What are the two faces of this vitamin? Well, the classical severe form of niacin deficiency is called Pellagra, which comes from the Italian meaning rough skin. And depending on whether you are an optimist or a pessimist, you say that Pellagra is the 3 Ds of dermatitis, dementia, and diarrhea. That's the optimist. Or if you're a pessimist, you say that Pellagra signs are the 4 Ds: dermatitis, dementia, diarrhea, and death. In the dermatitis, it is specifically skin sensitive. It begins with reddening, and eventually, as it becomes more severe, can progress to scaling and a very dark color in the skin. It spreads symmetrically across areas of the skin that are exposed to sun. The most common areas, based mainly on the pattern of sun exposure, are the backs of the hands, the wrists, the forearms, the face, and the neck, right? The places that you have the most exposure to the sun. It does not manifest without sun exposure. You can have pellagra and not have the dermatitis if you're just not exposed to enough sun. With that said, the dermatitis of pellagra often coexists with the cutaneous manifestations of riboflavin deficiency, meaning all the things that we talked about in the last episode, actually 2 episodes ago in episode 58, with the crusting around the lips, the cracking at the corners of the mouths, the inflamed skin around the edges of the nose, and so on. The tongue often bright red, swollen, and painful. And the reason that riboflavin and niacin deficiency coexist is because riboflavin deficiency can cause niacin deficiency, because riboflavin is involved in the synthesis of niacin from protein, as we will see. But also, niacin causes malabsorption. Niacin deficiency causes malabsorption of many nutrients, and that can include riboflavin. The second D, or dementia, begins with general depression. eventually, when it becomes severe, it progresses to schizophrenia-like psychosis with auditory and visual hallucinations and paranoid, suicidal, or aggressive behavior. It disappears very rapidly in response to niacin. So there's been a lot of interest in niacin supplementation for schizophrenia because the manifestations of schizophrenia look so much like the psychosis of niacin deficiency, but niacin hasn't been very helpful in schizophrenia. You know that it's not pellagra psychosis, pellagra dementia, if the niacin doesn't resolve it, because when the dementia is due to niacin deficiency, resolving niacin deficiency causes almost immediate resolution of the problems. In the neurological disorders, you can also have, when it gets severe, tremors or muscular rigidity, loss of the tendon reflexes, numbness and weakness. And it's thought that there's a very significant chance of you being locked up in a mental institution with no recognition that you have the deficiency, especially if you're not outside a lot and you don't get exposed to sun. Because imagine that, first of all, you could have pellagra if you are just depressed, because the end stage, the worst case of it, is the schizophrenia-like symptoms, but the early stage is just depression. And if you are depressed and you correct a niacin deficiency, the depression will go away because even the schizophrenia-like psychosis just goes away. But if you are depressed and you have no idea that it could be niacin and you never try it, you could have ongoing depression for a very long time that would respond to niacin, but you have no idea that it would because you never tried it. And in fact, that could be the very earliest sign of pellagra, and you might not have any of the other signs because you're not exposed to enough sun to get the dermatitis, and you're not deficient enough to get worse than just general depression. And what's interesting is that in the historical epidemic of pellagra that occurred largely after Columbus found corn in Central America and spread its use throughout what became the United States and throughout Europe, but didn't realize that the traditional processing of the corn by the natives was needed to free the niacin that was bound in the corn. What's fascinating about those historical epidemics is that in the southern United States, where the climate was warm and people were outside all the time, they developed the classical dermatitis. But in Europe, where the weather was colder and people were not outside as much, they didn't. They just got the dementia. And it's thought that historically in Europe, pellagra was very underdiagnosed because people just had dementia or they were just psychotic, and it was much harder to tell that they had niacin deficiency because they didn't have the characteristic skin signs that are so much more obvious by looking at the person. The third D of pellagra is diarrhea. This is the least specific sign because you can have diarrhea for 1,000 different reasons. So having diarrhea could mean you have pellagra, but it tells you almost nothing about the probability of that being true, absent the dementia or dermatitis. The diarrhea is particularly pernicious, though, because it causes a vicious cycle of nutrient deficiencies. If you have diarrhea, you will eventually become deficient in zinc. If you have diarrhea, you will eventually become deficient in so many other nutrients that often pellagra exists with many nutrient deficiencies at one time. The fourth D, death, occurs when you don't treat the pellagra. Besides these classical deficiency signs, there are a number of things that we might expect suboptimal niacin status to do based on either things that we know it does in the body or results of supplementation. So we could expect suboptimal niacin status to be involved in fatigue, exercise intolerance or poor exercise performance, accelerated aging, especially of the skin in response to the sun, but aging faster in general. Cancer and inflammation of the esophagus, vulnerability to leukemia, increased genetic mutations, potentially leading to negative effects of aging or conceivably birth defects, but I don't know if any clear evidence making that connection, and skin cancer are all things that we could potentially associate with suboptimal niacin status. Now, the flip side of niacin deficiency is niacin toxicity. In fact, niacin has an LD50 in rodents, which means that it can kill rodents, and we can characterize what is the dose of niacin that leads to the death of 50% of rodents. That's a standard way that you assess the lethality of a toxin. The LD50 is so high that it's completely irrelevant to what humans are taking now, but there are many factors related to toxicity or excess niacin that are very relevant to what people now experience. The most common and famous of these is the flushing response. The flushing response involves redness, itching, and if it gets really bad, it can progress to blistering and brown color of the skin, nausea, vomiting, and headache. The nausea, vomiting, and headache are probably more related to the liver toxicity than to the flushing response. And in general, this is nicotinic acid form of niacin. We'll talk about the different forms of niacin in a little bit, but usually this is nicotinic acid supplements that are used to lower people's blood lipids. That's what's leading to this. Niacin can also worsen glucose tolerance. It can elevate homocysteine, and it can cause liver damage. In the early stages of this, you might see elevated liver enzymes, hepatitis, jaundice, but you can see, in the worst cases, encephalopathy and liver failure. In rarer cases, there are some effects in the eyes, like blurred vision, lazy eye, but the effects in the eyes are every time it's been reported, it's been completely reversible by just taking the niacin out. Now, just as we could speculate about suboptimal niacin status signs based on what it does in the body, we could also speculate about other effects that are not as obvious, but are a result of too much niacin. And that's because niacin is detoxified using methylation, which means that excess niacin, even before it causes any direct toxicity of the types that we were talking about here, is going to start reducing your methyl group supply. If you don't have a background in methylation, then check out my page on methylation, chrismasterjohnphd.com/methylation. But in brief, methylation is very important to mental and physical health. Methylation is overwhelmingly the most sensitive thing that a decrease in methylation status will do is cause lowered synthesis of creatine. And creatine plays many important roles in the body, but it's most famous for supporting exercise performance. So poorer exercise performance is one of the things that you could see from a reduced creatine synthesis, especially if you're not supplementing with creatine on your own for the purpose of exercise performance. Creatine supplementation has also been shown to improve depression in women, taken at the same dose, 5 grams a day, that all the athletes are taking for exercise performance. And that might be because creatine plays a role in energy metabolism in the brain, just like creatine plays a role in energy metabolism in the muscle. But it might also be because when you supplement with creatine, you reduce the number of methyl groups that you need, and you have more methyl groups left over to regulate your neurotransmitters. So just like we might expect too much niacin to sap your methyl groups and lower your creatine synthesis, we might also expect sapping the methyl groups to affect your neurotransmitters. How exactly would they affect your neurotransmitters? Well, if you want to know the details on this, Google my name with methylate your way to mental health with dopamine. The short end of it is that when you methylate dopamine more, you tend to have a more flexible mind. When you methylate dopamine less, you tend to have a more stable or rigid mind. Either of those can be just personality traits when they're in the middle and they're just varying a little bit. But when you get to the extremes, both of them can cause problems. And too much niacin sapping your methyl groups and affecting your dopamine, you would expect that to make you more mentally rigid. You would expect negative thoughts and thought patterns, for example, to get more easily stuck in your brain. And that might not automatically make you depressed, but if those are depression-producing thoughts, you'll be more vulnerable to depression. And if those are anxiety-producing thoughts, you'll be more vulnerable to anxiety. This sapping of methyl groups is thought almost universally to be the mechanism of causing liver failure. Because another thing that happens when your liver is depleted of methyl groups is you get fatty liver disease. Another thing that happens is that you lose the phosphatidylcholine that you need to make up your cell membranes. So you have fatty liver, you have dysfunctional cell membranes, and at extremes, you would expect a severe dysregulation of gene expression because you use methyl groups to regulate your gene expression. So through those mechanisms, the severe sapping of methyl groups is probably what underlies the liver damage, while a more moderate sapping of methyl groups could easily explain something like Jane had experienced. Remember, in Jane's story at the beginning, Niagen at first is increasing, and this is an actual story. I changed the name, but someone wrote this out on my Facebook page. So this is a true story. This person was using Niagen and at first got benefits from the energy, but then the energy started to tank and the mental vulnerability started appearing. Well, what was going on? Probably the Niagen was increasing the role of niacin in energy metabolism, improving her energy metabolism, but it was also sapping her methyl groups, and eventually that led to decreased creatine synthesis. So now you have lowered energy in your muscles, and that led to less methylation of dopamine, leading to increased vulnerability to mental disturbances like depression and anxiety. If we look at the story of John had increased risk of liver failure to begin with because of the diabetes and the non-alcoholic fatty liver disease. As Alex will talk about later, the immediate release nicotinic acid that he was first put on is more likely to cause a flushing response, but the slow release niacin that he was later put on, that he was able to increase the dose with, got rid of the flushing response, but it also caused more liver toxicity. And that liver toxicity, of course, being because it went through the methylation pathway more, and Alex will explain more details about that later. And then as he increased the dose up to doses that have been reported in cases of liver failure. Now that's reconstructed by me from the case report literature, not an actual true story, but it's true to the principles that you see in the case reports. The story of Julie is a case of very moderate pellagra. So she's on a diet that we will eventually see is that one of the diets that you would expect to cause niacin deficiency. It's not an extreme niacin deficiency, but it's that early stage pellagra dementia where all it occurs, the only manifestation you see is the depression. The sun exposure, the ultraviolet light exposure is starting to cause early pellagra symptoms in the skin, which could just be reddening on the back of the hands, but it's not severe enough to cause the more obvious and distinct classical skin signs that you would see in pellagra, just the beginnings of it. So because she shies away from the light, the skin signs never get worse. They just get better. And then, but the mental degeneration continues. And perhaps because of the SSRI, sometimes that can provoke, or at least in theory could provoke, a more extreme psychosis. Or maybe the SSRI is irrelevant. I just threw it in there. She progresses to the later stages of the pellagra dementia, and because she only has the mental symptoms, she gets diagnosed as schizophrenia and never gets properly diagnosed with niacin deficiency. This story I made up, but I made it up being true to the principles that you would find in the literature. So now let's get into some of the more scientific detail around why would niacin have these effects. And we'll start with the chemistry of what niacin is and move into the biochemistry of how we use it, and then the biochemistry of how we get it. So niacin, like riboflavin, can easily gain or lose electrons, and that allows it to participate in redox reactions. Niacin exists as two main vitamers. A vitamer is when a vitamin exists in different chemical forms. The first vitamer is nicotinic acid. The second vitamer is nicotinamide. We could say that nicotinic acid is essentially the plant form, while nicotinamide is essentially the animal form. It's not quite as black and white as something like beta-carotene being the animal form, the plant form of vitamin A, and retinol being the animal form of vitamin A. That's where you just see zero retinol in plants and almost no beta-carotene in animal products, except traces of it that they ate from the plants. It's not that black and white with niacin, but it's fairly close. So 95% of the niacin in plants is nicotinic acid, whereas 85% of the niacin in most animal products is nicotinamide. So the overwhelming proportions. Nicotinic acid has to be converted to nicotinamide to be used. I'm not 100% sure why this is, but the chemistry part of my brain wants to speculate like this. An acid is, when it's mixed into solution, carries a negative charge. The role of nicotinamide is to accept negative charges in the form of electrons that can be used to harness the energy that is stored in the electrons of the food we eat. Nicotinic acid, it would seem, would not be able to accept electrons because it's negatively charged, and electrons are negatively charged. Negative repels a negative. So you have to neutralize that negative charge to actually make nicotinamide a good electron acceptor. Now you might ask, then what the heck is nicotinic acid doing in plants? Well, in plants, nicotinic acid is used for nicotinamide and does play the roles in energy metabolism that it plays in us. But the nicotinic acid is also used to synthesize many different alkaloids that play many different roles in the plants, such as pest resistance or regulating their growth. So nicotinic acid has many roles in plants and zero roles in humans and animals. In plants, one of the things that nicotinic acid is used for is to make nicotine. And this explains why niacin and nicotinic acid have their names. So historically, nicotine drew its name from the French ambassador to Portugal, Jean Nicot. And my French is bad, so I don't know if I pronounced that right. But Nicot is the basis for the word nicotine. He brought tobacco seeds back to France in 1561. Since he was associated with tobacco and tobacco contains the drug nicotine, then nicotine was named after him. Nicotinic acid in plants is the precursor to nicotine. It's structurally related to nicotine. And so it was named nicotinic acid. But then in 1942, the American Medical Association realized that it would be a big problem if people associated the vitamin B3 with nicotine, because people would think they could get vitamins from smoking cigarettes, and they would think that vitamins were bad for you like cigarettes are. So they coined the term niacin, taking the ni from the ni of nicotinic acid, taking the AC, the second syllable, ni-us, that comes from acid, and then in is just the ending to the word, just like vitamin. So niacin derives its name from nicotinic acid, in turn deriving its name from nicotine. But mechanistically, in our bodies, nicotinic acid has nothing to do with nicotine. So niacin has none of the actions that nicotine have. And in fact, there are even receptors for acetylcholine that are called nicotinic receptors. Those do respond to nicotine and have nothing to do with the actions of nicotinic acid. So we must convert any nicotinic acid in the diet into nicotinamide in order to serve the physiologically essential functions of niacin in our bodies. Nicotinamide is the form that we use. In episode 58, we talked about riboflavin, and we talked about how riboflavin was structurally related to the building blocks of DNA. Well, the same thing is true of niacin. So nicotinamide is a nitrogenous base, just like flavin from riboflavin is, and just like adenine, which is used in DNA, RNA, and to make ATP is. Nicotinamide riboside is the nucleoside form that has ribose added to it. Nicotinamide riboside is equivalent to riboflavin, the vitamin that we consume, or to adenosine. Nicotinamide mononucleotide is a nucleotide. This has ribose and a phosphate added to it. Nicotinamide mononucleotide is analogous to flavin mononucleotide, or FMN, also known as riboflavin 5-phosphate that we discussed in episode 58, or to adenosine monophosphate, AMP. Just as when we talked about riboflavin, we talked about FMN joining to AMP to make FAD, it's also the case that for us, we take NMN, or nicotinamide mononucleotide, and we join it to AMP, and we get NAD. NAD is the main physiologically essential building block of all niacin biochemistry. All of it goes down into producing NAD. You'll notice a little bit of a difference to riboflavin here. So the nitrogenous base, flavin or nicotinamide, for riboflavin, we don't consume flavin. We only consume riboflavin. So we consume riboflavin at the step of the nucleoside that contains the ribose. For niacin, that's not true. Niacin, we're generally starting with the base, with nicotinamide or nicotinic acid. And the thing that's analogous to riboflavin is nicotinamide riboside, which is generally not found in the diet except in trace amounts in milk. So there's a little bit there in milk, but generally we're not eating nicotinamide riboside unless we are specifically supplementing with it, which actually is becoming more and more popular. Unlike riboflavin, niacin is very narrow in the scope of its oxidation states. It's not photoreducible, meaning it's not damaged by light. It doesn't require being enveloped in proteins to protect it from light, like riboflavin does. And in general, in biochemistry, although you will sometimes find niacin bound to proteins, in general, NAD is acting as a diffusible carrier of electrons. So like I mentioned when we talk about riboflavin, quite often niacin and riboflavin are participating together in a reaction. The FAD taken from riboflavin will be part of the protein and will participate in the transformation of whatever that enzyme is carrying out. Whereas the niacin will be the thing that carries the electrons to that enzyme or takes the electrons away from that enzyme to go somewhere else. The scope of what we do with niacin in the body biochemically is broader than what we do with riboflavin. So let's talk a little bit about the biochemistry to get into the uses. The first and main thing that's been known the longest is that we use niacin for redox reactions, just like we use riboflavin for the same types of redox reactions. That means taking electrons from one place to another. And the reason redox reactions are so essential is because in our food molecules, energy is stored in the chemical bonds. The chemical bonds, by definition, are the shared electrons. We need to rip apart those food molecules to harness those electrons and siphon the energy out of those electrons. That's the whole basis of our energy metabolism. Now, first of all, NAD can be converted by NAD kinase using zinc, magnesium, and ATP to make NADP. NAD and NADP are only distinguished by an extra phosphate on NADP, hence NADP. NAD is mostly maintained as in the oxidized state, meaning NAD plus instead of NADH. NADP is mostly maintained in the reduced state, meaning NADPH instead of NADP+. We functionally use these in a distinct manner. Overwhelmingly, NAD is used for catabolic reactions that oxidize things, like oxidizing our food molecules to rip them apart and harness their energy. NADP is overwhelmingly used for reduction and for anabolic things, so building up things or recycling them. As examples, NADPH is used to recycle glutathione, the master antioxidant of the cell, and the master detoxifier. It also plays a role in other detoxification processes mediated by cytochrome P450 enzymes. It's critical to antioxidant defense, as I just mentioned, through glutathione recycling, but it also recycles nutrients like vitamin K and folate, and it's used in the anabolic synthesis of fatty acids, cholesterol, neurotransmitters, and nucleotides. If we look at NAD, one thing that we'll see if we compare it to riboflavin is that NAD is far more universal in energy metabolism. We talked about how burning fat required twice as much riboflavin as burning carbohydrate. Burning fat and carbohydrate require the same amount of niacin in the form of NAD. Even if you look at the most extreme form of energy metabolism, anaerobic glycolysis. Anaerobic glycolysis is converting glucose to lactate in order to harness ATP when all your other options aren't available. You do this when you're exercising extremely intensely and you need more energy than you can possibly get using oxygen to fully break apart your food molecules. And you use it in certain tissues that have poor exposure to oxygen. Or you use it in some tissues that don't have any mitochondria, like red blood cells. Even in anaerobic glycolysis, you can do this without any oxygen. You can do this without any riboflavin, and you still need NAD, right? So all energy harnessing in everywhere requires NAD. In addition to this universal role in energy metabolism, there is a huge portion of NAD metabolism in a completely separate, distinct sphere. And this is NAD is often broken down to form Adp-Ribose. Remember, when we formed NAD, we took nicotinamide and we added AMP. So the adenine of ADP is already stuck together in that molecule. It's part of NAD. So we can break apart NAD to generate nicotinamide and in the process generate Adp-Ribose. Adp-Ribose is used for a number of things that include the repairing of DNA, the response to cellular damage, and regulating many different processes. So the most famous of these is the poly-Adp-Ribose chains made by Parp enzymes that are critically important for DNA repair and longevity. There are many Parp enzymes, but I'll talk about two of them that are most famous, Parp1 and tankerase. Parp1 is a zinc-dependent enzyme that makes strands of Adp-Ribose. It's called poly-Adp-Ribose because you're just taking one Adp-Ribose and you're just making a chain of it stuck together. To make poly-Adp-Ribose, every time you make the Adp-Ribose to lengthen that chain, you need to hydrolyze, break apart another NAD molecule. As you lengthen this chain, you have an accumulation of negative charge, and you also have an accumulation of this big obstructive chain. The Adp-Ribose chain itself is taking up a lot of room. What you can do with that is you can pry open the strands of DNA to allow the repair machinery to access those strands. So Parp1 actually acts as a monitor in the cell for DNA damage. When it senses the DNA damage, it immediately goes over to the site of DNA damage, starts breaking apart NAD to generate Adp-Ribose. It strings together the Adp-Ribose and uses it to start prying apart the strands of the DNA. Another interesting aspect of this is that it adds the Adp-Ribose to itself, and eventually when the chain of Adp-Ribose on itself gets big enough, it pries itself off of the DNA, and that's what allows the repair machinery to come over and fix the DNA. So if you let's imagine that you are only a little bit deficient in NAD, what's going to happen is you will sense the DNA strand breaks or damage. You will go over there with Parp and start making this Adp-Ribose strand, but it'll never get big enough for you to, if you are the Parp enzyme, right? Your strand will never get big enough for you to pry yourself off of the DNA. And so all you did was go over there and get stuck, and you're just blocking the DNA repair machinery. If you're really deficient in NAD, you're not even going to sense the DNA damage. You're not going to do anything about it. And the DNA damage is, if anything, just going to continue and get worse and replicate itself. So even being a little bit of NAD deficient is going to hurt this process. Parp 1 is most famous for playing a role in DNA repair, but it also is able to bind to structures in DNA that are not damaged and allow gene expression machinery to access the DNA. So it plays a role in gene expression, and that's been demonstrated to play an important role in neuroplasticity and learning. It also plays a role in the inflammatory response that could be bad in situations of chronic inflammation, but is good if you have an infection. Parp 1 is one of the Parps. The Parps are a family of enzymes, and there's another Parp called tankerase. Tankerase does basically the same thing that I just described, only instead of trying to open up the DNA to allow the DNA repair machinery to get in, what it's doing is it's opening up the ends of chromosomes called telomeres to allow telomerase to get in. And what telomerase is going to do is to lengthen the telomeres. One of the leading theories of aging is that cells can only divide so many times because every time they divide, they lose these little protective caps on the ends of their chromosomes called telomeres. By having better NAD status, you allow tankerase to open up the ends of the telomeres and allow telomerase to get there so it can lengthen them. That will theoretically slow the aging process by allowing your cells to divide in a healthy way a greater number of times. The second famous example of an NAD-consuming enzyme are the sirtuins. Sirtuins are enzymes that are involved in regulating how compact the DNA structures inside of our cells are. So our genes are sequences within DNA strands, but those DNA strands are then wound together around themselves like a ball of yarn. And in order to access the genes to express them, you need to open up that ball of yarn a little bit, which is called, this ball of yarn we call chromatin. So opening up that ball of yarn is called relaxing the chromatin structure. We want it to be compact if we want to protect ourselves from DNA damage, but we want it to be open if we want to express the genes. And if the genes get damaged while they're being expressed, we have to open it up even further. So the Parp enzymes are using Adp-Ribose to open up the genes, the chromatin even further to allow the DNA repair machinery to come in. But whenever we do not need to do that, and whenever we don't need to be expressing a gene, we're using sirtuins to do the opposite by making the chromatin more compact. And so what happens is there's a playoff between the Parps and the sirtuins. The sirtuins are going to make the chromatin more compact. The Parp enzymes are going to open it up more. And both of those and the balance between them play an important role in protecting the DNA from damage that would occur with aging and with chronic insults by being exposed to more stress. On top of this, we also have Adp-Ribose, not as a string, not as a long strand of polymer, but just a single Adp-Ribose is often regulating protein function. And there are enzymes called, the enzymes that use these are called Adp-Ribosyl transferases, or ARTs. There are ecto-ARTs that use NAD outside the cell, and there are endo-ARTs that use NAD inside the cell. And these are involved in regulating many different proteins. One thing that's interesting about the ecto-ARTs is that they're using extracellular NAD. And there are people who are injecting themselves with NAD to increase the NAD in their blood, which is extracellular, who are reporting intense reactions to that. So Ben Greenfield, for example, uses this, and in the IV, he does a little bit of drip at a time over the course of, I think it's 10 minutes. I might be misremembering that. But these little drips are because there is an acute vasodilatory and inflammatory response to that. Well, why is that? Because the ecto-ARTs use that NAD to make Adp-Ribose and regulate proteins on the outsides of cells. And one of the cells that are most responsive to those are granulocytes, part of the immune response. And activating those granulocytes with extracellular NAD will provoke vasodilation and an inflammatory response. Why? This isn't really worked out yet, but it appears probable that extracellular NAD is released from dead and dying cells or from cells that want to communicate something about their energy status. We're not sure exactly what that is, but that it's some sort of stress response that is then activating, among other things, the immune response. NAD can be taken up into cells. There's clear evidence that I'll cite in the show notes, but it seems to be a signal. The last thing that I'll talk about is the metabolites of NAD that are involved in regulating calcium transport. In probably all cells, the intracellular calcium concentration is kept exceedingly small. And that's because influxes of calcium are used as a signal to make something happen. In the case of neurons, we know that the calcium coming into the cell at a synapse is the universal signal that allows a neurotransmitter to be released. NAD is used to produce cyclic Adp-Ribose, linear Adp-Ribose, O-acetyl Adp-Ribose, and in addition to all this, NADP can be converted into the deamidated form. In other words, the form that looks just like the plant form called nicotinic acid adenine dinucleotide phosphate, NAADP. And all four of these things are involved in stimulating the transport of intracellular calcium. So in neurons, part of the signal to allow you to release a neurotransmitter is to release cyclic Adp-Ribose, linear Adp-Ribose, O-acetyl Adp-Ribose, and NAADP, all of which are made from NAD, all of which act to allow calcium to come into the cell and, boom, make the neurotransmitter go out. So how do these things explain deficiency? Well, the dermatitis is caused by being exposed to the sun. Even normal exposure to the sun is always causing little bits of DNA damage in your skin. And you are always reacting to that by breaking down NAD to repair that DNA damage using the Parp enzymes. And if you are niacin deficient, then you will not have enough NAD to repair that damage. And what you start to see is that just the normal exposure of sunlight, of you going outside, starts to cause obvious manifestations in your skin of DNA damage. Now, you can imagine from this that when you're not niacin deficient, that's happening all the time. Like, we go outside, I go outside every morning and drink my coffee in the sun for my circadian rhythm. I'm getting DNA damage and I'm using up NAD. in order to fix it. The diarrhea. Part of this is that you just don't have enough energy. You cannot efficiently break down your energy in food in order to support the high turnover rate of the cells in your intestines. In your intestines, you have finger-like projections called villi, and then you have even tinier projections on top of those called microvilli. And at the very tips of the villi, you have cells that are turning over every 3 to 4 days. So you're investing this enormous amount of energy in producing all these cells all the time. And then just in their metabolism, right? Because the absorption of so many nutrients is energy intensive. So these are highly energy using cells that have a very high rate of turnover that have to reproduce themselves all the time. So there's enormous consumption of energy just to maintain your GI tract. And in niacin deficiency, the supply of that energy falls apart. You don't have the energy to maintain those finger-like projections. And so you get something that looks very much like celiac disease, except instead of being caused by an autoimmune condition where the villi are attacked, you just don't have the energy to make the villi and maintain them. The other thing that I think is probably true, and I wouldn't have realized that this except that just this year, a mouse study that had very elegant tracing of where NAD goes in the body showed that in the small intestine, you have the highest rate of NAD consumption is in the small intestine and the spleen. And when I say consumption of NAD, I'm talking about actual breakdown of NAD for the Parps and for the Parps, the sirtuins, and all the processes that I was just talking about. If you are going through NAD at 40 times the rate in the small intestine as you're going through it in other tissues like the muscle, for example, then probably the diarrhea and niacin deficiency is also caused by the loss of that capability. Why are you blowing through so much NAD? Well, I imagine that just like your skin, your small intestine is facing the outside of your body. Like inside your mouth and inside your GI tract is the outside of your body. That's inside your body is highly regulated. Once you cross the intestinal barrier, you've been very selective about what you allow in there. But your small intestine is exposed to everything in the environment, just like your skin is. And so I think the skin and the small intestine face these huge insults that require such tremendous turnover of NAD that they are among the things that suffer most when your NAD is in short supply. The dementia could in part be because through regulating gene expression, the Parp enzyme plays an important role in learning and memory. And because Adp-Ribose addition of proteins will regulate how sensitive neurons are at the synapse to neurotransmitters. But it seems to mostly be because of a loss of those 4 calcium regulating metabolites, the cyclic linear O-acetyl Adp-Ribose and the NAADP. Part of the reason that it seems to be the signaling of value of those that are lost is that it responds so fast to niacin when you fix it that it just seems almost certain that this immediate response regulating the immediate acute release of a neurotransmitter has to be the most important thing there that's missing, because otherwise it would take a longer time of niacin repletion to start repairing all the damage that's been done. And in fact, it's just, boom, you take the niacin, all of a sudden you feel better. All of a sudden you remember all the delusions that you had when you were psychotic a few moments ago. It's very, very quick. And so it's probably a result of losing these signals that control neurotransmitter release. Okay, now let's talk about the biochemistry of how we get niacin from food and how we get rid of excess niacin from our bodies. That'll help us understand both how we nourish our niacin status and how we avoid the problems of toxicity. So the pathways to NAD synthesis are different depending on whether we're getting niacin from animal form, from plant form, or from protein. If we synthesize NAD from the nicotinamide, predominantly found in animal products, we use 2 steps that require magnesium, ATP, and in some cases, if we synthesize NAD from plants, from the nicotinic acid that predominates in plants, we are using 3 steps instead of 2, And in addition to magnesium, ATP, and zinc, we're using potassium and the amino acid glutamine. If we synthesize NAD from protein, we have to go through 9 steps. And the first 8 steps of these are unique to this pathway, and they require iron, riboflavin or vitamin B2, and vitamin B6. Then the final step is the same step that we do when we convert the plant form into NAD, and that requires magnesium, ATP, potassium, and glutamine. For niacin, we have to have a way to get rid of excess nicotinamide, and the reason is as follows. All the enzymes that I talked about before that make Adp-Ribose, the ones that are involved in protecting your DNA from damage, repairing damage to your DNA, and lengthening your telomeres to presumably extend your life, these all require NAD and release nicotinamide. But nicotinamide inhibits those enzymes through product inhibition. It's a negative feedback loop. And that means that in order for those enzymes to function correctly, we need to get rid of the nicotinamide that results. And we do that through one of 2 ways. Our first and best way is to take the nicotinamide and convert it back into NAD+. That's called the Selvage Pathway. But to do that requires ATP and it requires 2 enzymes. If we can't convert nicotinamide into NAD fast enough, then we need to clear it through detoxification. The way that we detoxify it is we methylate it to 1-methylnicotinamide, and then we might oxidize it further to several metabolites. And in a very, very minor pathway, we might just oxidize it to break it down. But overwhelmingly, what we're seeing is that we methylate it, and then we urinate out those methylated metabolites. There are 2 or 3 methylated metabolites that appear in the urine, and we can use those as markers of niacin status, as we'll talk about later. Nicotinic acid has its own detoxification pathway, and that is that it is conjugated to glycine, an amino acid, that generates nicotinic acid, which is named because it's the form of nicotinic acid that winds up in the urine, so nicotinic acid. So these detoxification pathways are super relevant to the toxicity that we can experience from any of these forms of niacin. So I'm going to have Alex come in now and talk a little bit about the mechanisms of toxicity. Alex, can you shed some light on how the degradation pathways tie into the toxicity of the different forms of niacin?
Yeah, so niacin is going to be metabolized primarily in 2 pathways within the liver. The first is going to be its high affinity amidation pathway that will use methyl groups to get rid of the niacin in the body. And this is going to be the first pathway that niacin is going to go through. It's the pathway that ultimately leads to the creation of NAD and all that stuff. The second pathway is more of a backup for when niacin saturates this amidation pathway, because the amidation pathway works very slowly. And by slow, I mean that it can metabolize about 40 milligrams of niacin per hour. And when you consider how much niacin someone would take, for example, to lower blood lipids, you're talking about 500 milligrams, 1,000 milligrams, several grams. And so this pathway can quickly become overwhelmed. So the backup system is to conjugate the niacin, or in this case, the nicotinic acid, with glycine so that it can be easily excreted. And it's the amidation pathway and its saturation that is going to cause the liver toxicity, because it's going to drain the liver of methyl groups in order for it to progress. And we can see that the fact this relies entirely on the draining of methyl groups suggests that niacin-induced liver toxicity can be completely circumvented by eating a diet that's rich in methyl donors and precursors like choline. So things like egg yolks, liver, all that good food.
Okay, so just to clarify this with what I was just talking about, the nicotinamide, if we're talking about taking nicotinic acid, we convert it to nicotinamide because we need to for its vitamin function, but that then feeds into the methylation pathway as the way we detoxify it. And if we could not convert it into nicotinamide, the vitamin part, fast enough, then that's where we're using nicotinic acid to glycinate it. Is that right?
Yeah, correct. And so this split between, or I shouldn't say split, but the ability of the niacin molecules, whatever form of niacin you end up supplementing, is going to determine not only the risk of liver toxicity, but also the risk of having a flushing reaction. And it's completely related to the fact that this methylation pathway operates so slowly. So when you take just regular basic niacin, in this case nicotinic acid, that is going to be absorbed very rapidly in 1 to 2 hours. And it's going to be metabolized at a rate of about 500 milligrams per hour. But only about 40 milligrams of that is going to go through the methylation pathway, and the rest is going to build up in the bloodstream and eventually get glycinated to get it out of your system. It's the buildup of that nicotinic acid that will bind to the niacin receptor that exists on immune cells, such as the Langerhans cells in the skin. And this is going to cause an inflammatory cascade that will ultimately cause that flushing reaction that you experience. The niacin receptor also exists on macrophages, monocytes, and neutrophils, and all of that plays into this flushing. Now, on the flip side, when you take something like niacinamide, you're not going to have a buildup of nicotinic acid because niacinamide is going to feed directly into the methylation pathway. Niacinamide is that first molecule that nicotinic acid needs to be turned into in order to create NAD.
So just to clarify, I should have introduced this earlier and I didn't. Nicotinamide and niacinamide are the same thing. And so on supplements, you'll often see niacinamide used as a word, whereas in if you're looking at the scientific literature, you'll more often see nicotinamide. But nicotinamide and niacinamide are the same thing.
Yeah, exactly. So niacinamide or nicotinamide is not going to cause that flushing reaction because you're going to have a huge buildup of it, but it has an affinity that for the niacin receptor that is 1/1000th that of nicotinic acid. And so there are a handful of studies out there showing that people who take niacinamide do complain about a flushing reaction, but it's definitely not consistent, and the lack of a plausible biological explanation makes me think it's almost placebo. It's also, in one study, there were like 2 people who took 100 milligrams reported a flushing, no one who took 500 milligrams, and then like 1 person who took 1 gram. So there isn't a dose response effect either, which just makes it seem all the more random that it occurred. So people don't like the flush, and that's understandable because, it's really annoying. And this led manufacturers to try to find a way around this. So the nicotinamide was one option to do that, but it doesn't have the same effects on blood lipids as regular niacin. So then people looked at making what's called sustained release, often sold also as flush-free niacin. And the most common form that they would put in there is inositol hexanicotonate. And this is basically 6 niacin molecules that are all bound together that when it enters circulation, you'll have little enzymes in your blood that pick off niacin molecules one at a time. And it'll stay in your circulation for up to 48 hours to let these niacin molecules be plucked away. And overall, it's metabolized at a rate of about 50 milligrams per hour, which means that most of it is going to feed right into that primary pathway of methylation. And this is the form of niacin that has been most consistently associated with liver damage, which is understandable because although you're not going to have a buildup of nicotinic acid that causes flushing, you're going to have significantly more of the nicotinic acid that's released from it feed into the methylation pathway that ultimately will damage the liver by draining it of methyl groups. What would be interesting and what I haven't seen is if two people were given the same dose of slow release niacin combined with one group having a, for example, choline rich diet while another group ate a choline poor diet, and to see if the rates of liver toxicity would be different between them. Because again, in theory, this adverse effect on the liver could be circumvented by eating a diet that's rich in methyl donors.
So that makes a lot of sense to me. And I did a short video, like a 5-minute video called Why You Should Be Careful with Niacin and Nicotinamide Riboside, where I talked about the true story that I shared at the beginning, who I pseudonymed Jane. I talked about her story, and I talked about this from the perspective of if you're taking 300 milligrams of nicotinamide riboside, you could basically take like 1 milligram of trimethylglycine, which is a methyl donor, for every milligram of niacin in the diet, and you're going to roughly supply the methyl groups that you'd use there. My rationale was just to prevent the negative effects on creatine synthesis and on regulation of neurotransmitters. But it seems to apply exactly the same here. You just have to use a higher dose. And generally, like a molecule of niacin and a molecule of trimethylglycine are fairly similar in size. So it's not exactly the same, but you could guesstimate it as like 1 milligram for every milligram. One of the things that came up as a question to me before that I didn't fully understand the detoxification pathway, so I couldn't answer, but I think I get it now, is would taking those methyl donors interfere with the specific benefits you're trying to get of the niacin that you're taking? So, for example, if I understand you right, at least from the flushing is totally mediated by the nicotinic acid, but that's also, we don't use nicotinamide usually for blood lipids because it's also the nicotinic acid that's primarily affecting blood lipids. Is that right?
Yeah, because it's going to be binding of the niacin receptor by that nicotinic acid that mediates many of these effects.
So is it the same? Is that the same receptor that is regulating the blood lipid and the flushing response?
That's correct. And when we talk about blood lipids later on in more detail, I will discuss this in more depth.
Okay, so for like right now, I think the point that I'm trying to wrap my head around is there's basically, you would not antagonize the pharmacological effect of the nicotinic acid on, and we can debate about whether we even would do this in the first place later, but assuming we are taking nicotinic acid for blood lipids, assuming that's a good decision, we're not going to antagonize the blood lipid lowering effect by supplying the methyl donors, because the methyl donors are to help you get rid of the nicotinamide, and they don't do anything to get rid of the nicotinic acid, right?
Yeah, correct. But this gets back to that short video that you did about being careful with niacin because it can sap your glycine away, and that has implications for like reducing glutathione activity because you need glycine to make glutathione, and if your body's going to use it all to get rid of a bunch of niacin, then that can have some far-reaching implications on liver health too. And that could explain why people taking regular nicotinic acid, although it's rare, liver damage is still reported. It could be that the effect is mediated through glycine depletion rather than just general methyl donor depletion.
Well, yeah, and glutathione, I mean, you would expect glutathione depletion to cause liver failure. You know, the main cause of liver failure in the United States is taking acetaminophen. Acetaminophen directly binds glutathione, and it's very clear from the mechanism that when you get to 90% glutathione depletion in the liver, that's when you get liver failure. And so it would seem that glycine depletion in the liver would do the same thing here. On the flip side, would you say that glycine could be now I know from what I've read that to mitigate the flushing reaction, they were using a drug that was very specifically targeting the specific prostaglandin that was produced, and it's not on the market anymore because of side effects. But there's some evidence that aspirin can help because through inhibiting prostaglandin synthesis. But let's say we don't like aspirin and we don't like those kinds of drugs. Number one, do you believe, based on what you know about how this works, that adding glycine could minimize the flushing? And then number two, is there any actual evidence of that, or is it only a speculation based on how it works?
Okay, so there's absolutely no evidence of that, and I don't think that adding glycine would help minimize it, because glycine isn't the limiting factor. It's going to be the body's ability to conjugate the niacin with that glycine, and that operates at about a 500 milligram per hour rate. What I can say is that niacin tolerance does develop. It's pretty well established that after about 1 to 2 weeks of starting at a low dose and gradually increasing, the flushing side effects become incredibly minimal and much more spontaneous. They won't happen consistently. And that's because the body, specifically the Langerhans cells in the skin, become desensitized to the prostaglandin D2 that is behind the entire inflammatory flushing reaction. I guess the analogy would be, insulin resistance. If you have a lot of insulin floating around in your blood all the time, then cells become desensitized to it because you don't want it to be working all the time. It's going to be the same way in your skin. You become desensitized to that the inflammation promoting molecule that causes the flushing. Whether this would have implications on immune health, because your body would be less sensitive to a necessary step to protect you from foreign invaders, I don't know. But that desensitization is well established.
So basically, the risk of nicotinic acid is that we could deplete our glycine levels, but only up to a point. So if we put in more nicotinic acid than that, extra glycine doesn't do anything for us. But if we toughen up and stick to our guns, the flushing response goes away. Yet, nevertheless, the fact that the flushing response will go away doesn't change the fact that many people stop taking it because they don't like the flushing response and they don't want to stick to their guns. So tell us a little bit about the extended release niacin that was developed. What was the rationale for that, and how does that fit into this picture?
So extended release niacin was first formulated as like the drug version. It's what the pharmaceutical company jumped on because they wanted a product that would minimize flushing but also minimize the risk of liver toxicity. So they made an extended release niacin that is most commonly known as Niaspan, although it is also now available over the counter in various wax matrix, which just slows our ability to digest and absorb the niacin, letting it go into our body at a slower rate. And it is absorbed at about 100 milligrams per hour. So it's, 1/5 of that of regular nicotinic acid, but it is twice as quickly absorbed and metabolized as the slow release niacin. So it is effective at reducing blood lipids. We have meta-analyses, this is the form most commonly used as an adjunct to statin therapy, that show it is effective both as a mono treatment and when combined with statins. And the effects are comparable to regular nicotinic acid. And the occurrence of flushing is much less, as is liver damage, although both do still occur, as we would expect, because there are going to be individual differences in, for example, how much nicotinic acid needs to build up before you experience the inflammatory reaction. And because it's still going to be metabolized at a much slower rate, 100 milligrams per hour, you're still going to have a good amount of feeding into the methylation pathway that could sap the methyl groups and cause liver damage in someone who is pre-exposed to having liver damage from a low base supply of methyl donors.
All right, so that gives us a good sense of how nicotinic acid depleting glycine and nicotinamide depleting methyl groups can explain the liver damage, and how unglycinated nicotinic acid escaping into the blood can explain the flushing reaction. Let's take a different spin on the degradation pathway now and examine the rationale for why would someone supplement with the currently trendy supplements nicotinamide mononucleotide, or NMN, or nicotinamide riboside, or NR. And if you look at this pathway, what's happening is as follows. NAD is what you want. NAD is what supports your energy metabolism. NAD is what enzymes like the Parps and the sirtuins use for DNA repair, DNA protection, telomere lengthening, longevity, etc. But when those enzymes like Parps and sirtuins use up the NAD to produce Adp-Ribose, they release nicotinamide. Nicotinamide you do not want to hang around because the nicotinamide will inhibit those enzymes through a negative feedback loop, and you have to get rid of it to have good enzyme function. So what you want to do is use what's called the Selvage Pathway. That takes nicotinamide and it goes back to NAD. In the first step of the Selvage Pathway, you go to nicotinamide mononucleotide, or NMN. There is a little shunt at this step where you can go from nicotinamide mononucleotide to nicotinamide riboside. The difference between these two things is nicotinamide riboside does not have a phosphate. Nicotinamide mononucleotide has that extra phosphate. And then the nicotinamide mononucleotide has to go up to NAD. So if you are salvaging nicotinamide through your own metabolism, you will go to NMN and then you'll go to NAD. Or you can go to NMN and you can go back and forth to NR, and then the NMN can move up to NAD. I'm not sure why the NMN and the NR interconvert with one another, but my suspicion is as follows. So both of these steps, to go to NMN and then to go to NAD, both of these require magnesium and ATP. Both of them require a certain amount of enzymatic activity. If you take NMN and you go to the side route to NR and back, you will, in the process, take that phosphate off and donate it to ATP. So going over to NR, to nicotinamide riboside, could be a way of locally preserving ATP when ATP is limiting. Eventually, you have to get back to NMN in order to get to NAD. Additionally, it might be the case that you're trying to get rid of the nicotinamide really fast, faster than you can synthesize NAD. Well, if your only intermediate is NMN, then at some point you're going to build up NMN to the point where you can't make any more, and you're not going to be able to clear that nicotinamide. Whereas if you have a way to put some of that nicotinamide mononucleotide, NMN, elsewhere as nicotinamide riboside, it acts as a release valve so that you can keep clearing the nicotinamide and you don't get this buildup of NMN that makes you stop being able to clear it. So the ability to interconvert the NMN and NR might be a way of locally preserving ATP and might be a way of allowing a release valve on this process so that you can keep sort of saving up on those intermediates to eventually convert them to NAD. If the amount of nicotinamide exceeds what you can clear in that pathway, in the NAD producing pathway, the good pathway, the high priority pathway, the high value pathway, then whatever nicotinamide is left over will be methylated to get rid of it. That does two things that you don't really want. One is that you lose the NAD from the body irreversibly. You can never get it back. And the second thing is that you're sapping your methyl groups, which, as we were just talking about, in the not so bad cases can lower your creatine synthesis and mess up your neurotransmitters, and the really bad cases can cause liver failure. So let's say that we didn't have NMN supplements and we didn't have NR supplements, and we just had nicotinic acid and nicotinamide. I'd be looking at this and I'd say, look, the nicotinamide is better than the nicotinic acid because the nicotinamide is what is ultimately converted to NAD. The nicotinic acid isn't. Everything about nicotinic acid supplementation says our ability to make that conversion has some limit to it. We should just get the nicotinamide. But now the new guys on the block are the nicotinamide mononucleotide supplements, NMN, and the nicotinamide riboside supplements, NR. What's the difference between taking nicotinamide and those two? The difference is that if you take nicotinamide, the first thing it's exposed to is the methylation pathway without needing to do anything else. You can very quickly lose it in that pathway and you can very quickly sap your methyl groups. If you take NMN or you take NR, in order to get around that place where you lose it, you must go to NAD first. Only then do you get used by the PARPs and the sirtuins to generate nicotinamide. Only then are you exposed to irreversible loss of the nicotinamide through methylation and irreversible sapping of those methyl groups from your methyl group supply. So in theory, it has to be the case that taking NMN or NR is going to get more NAD and less loss, both less loss of the niacin itself and less loss of the methyl groups. And to get it, like, let's compare this to two other vitamins to get a sense of what this turnover means. So when we were using riboflavin, everything we're doing is redox reactions. We don't consume the riboflavin in redox reactions. We lose a little bit through light-mediated degradation mostly. In this case, some giant proportion of our NAD is being consumed by these enzymes. In fact, it's estimated that the average molecule of NAD lasts about 8 hours, and that in the liver it lasts about 2 hours. And so if you look at the requirement for riboflavin and the requirement for niacin, if you just compare the RDAs, the RDA for niacin is 12 times more than the RDA for riboflavin. And a molecule of riboflavin is 3 times the size of a molecule of niacin. So basically, molecule for molecule, we need 35 times more niacin than we need riboflavin. Even though in energy metabolism, they're doing like the exact same thing, all that massive need for niacin is because of this loss and turnover in the detoxification pathway, because we're generating nicotinamide that is lost through methylation faster than we are able to resynthesize NAD with it. Now, compare it also to taking methylfolate supplements. I've criticized methylfolate supplements because even though, yes, methylfolate is one of the main forms you get in food, and yes, if I'm going to take a folate supplement, that's probably what I'm going to take, the idea that the methyl group on that methylfolate supplement is making a big dink in your methyl group supply is kind of ludicrous, because every molecule of folate that you have gets a methyl group added to it 18,000 times a day. By contrast, if your average NAD molecule lasts 8 hours before it turns over, that NAD is only turning over about 3 times a day. So it makes a lot of sense to say, hey, maybe getting better NAD synthesis from NMN or NR actually means a lot when every extra molecule of NAD that we get is going to last 8 hours in our body. That makes a lot more sense than trying to get, methylfolate molecules that are going to last milliseconds. But just how sensible are NMN and NR? In order to really wrap our minds around this, we have to answer the question, if you take these orally, do they get into the cells that we're trying to get them to? And I think what we'll see is that of the two, NMN probably does not get absorbed intact, while NR probably does. But let's back up from this discussion specifically of NMN and NR, and let's look now at the physiology of niacin. When we absorb it, what are we doing with it? Where are we putting it into our body? What are the organs that are involved in regulating where everything is going to? Okay, so when we first eat food, we start absorbing some nicotinic acid and nicotinamide in the stomach rather slowly. we have NAD and a tiny bit of NADPH that's in our food. We are not absorbing that in the stomach at all. Then these things get into the small intestine. Now we start getting very quick absorption, but first, before anything happens, we have phosphatases that cleave off the phosphates on these things in order to absorb them. We saw the same thing with riboflavin. This was my rationale for why I backed away from riboflavin 5-phosphate supplements in episode 58. I said it made sense to me until I really studied the details of the intestinal absorption, and I really don't believe that riboflavin 5-phosphate gets absorbed intact. Well, everything about how niacin is absorbed suggests that the phosphorylated form of niacin, the nicotinamide mononucleotide, the NMN, is going to be cleaved. The phosphate's going to be removed from it in the intestinal tract. The NAD, the NADPH in the food will be digested down into the unphosphorylated forms. That means that we are mostly in the small intestine. We're absorbing nicotinic acid. We're absorbing nicotinamide. And nicotinamide riboside is not usually in food, except traces in milk. But when we take it as a supplement, it's probably absorbed intact because unlike NMN, it doesn't have that phosphate that would be removed. It doesn't even matter if the transporters for these things exist in the intestines, because unless you have serious intestinal damage, you have this enormous abundance of enzymes that will just break off all the phosphates from everything that's phosphorylated in your food. Now, the first thing to happen is the nicotinic acid or the nicotinamide, and probably nicotinamide riboside, get into the small intestinal cell, which is called an enterocyte. There, we convert what we can of the nicotinic acid into nicotinamide. That nicotinamide, whether it came from nicotinamide in our food or nicotinic acid in our food or nicotinamide riboside, whatever it is, we're trying to get it into NAD in the enterocyte if we can. Whatever does not generate NAD goes into the portal vein into the liver. That is mostly going to be nicotinamide. It's going to be a little bit of nicotinic acid. The liver is going to take up, and when I say a little bit, I mean when we're eating food, right? If we're taking mega doses of nicotinic acid, then obviously we're getting a lot of nicotinic acid into the liver. But when we're just eating normal doses in food, nicotinic acid is the minor product that goes through the portal vein. Nicotinamide is the major product. The liver takes up what there is, converts the rest of the nicotinic acid to nicotinamide, converts whatever it can from all of those pools into NAD. And the NAD does two things. One is the NAD is used by the liver as NAD. The second is that the liver holds on to NAD as storage to later nourish the systemic circulation. The third thing is that the liver hydrolyzes some of that NAD down to nicotinamide, and it sends the nicotinamide out into the bloodstream to nourish the rest of the tissues. Almost exclusively, what you find circulating in the blood, in the extracellular fluid of the blood, not in the blood cells, but in the water of the blood, is nicotinamide. That overwhelmingly what's happening is the nicotinamide was generated by the liver for the specific purpose of nourishing all the other tissues. Do you have other things in the blood? Sure, especially if you take supplements. For example, if you take nicotinamide riboside, there's experiments in mice suggest that there's very trace amounts of nicotinamide riboside that wind up in your blood. Mostly, what winds up in your blood when you take nicotinamide riboside is nicotinamide. There's a little bit of NAD in your serum, in your plasma, outside your blood cells. And as I mentioned before, that is probably, unless you're injecting it, definitely not from eating it. Whatever NAD is in your blood is released by cells, probably dead cells, dying cells, or stress cells. Maybe cells releasing it as some kind of indicator of their energy state, and it's playing a signaling role, especially the most well-demonstrated of this to stimulate granulocytes to make an inflammatory response. So the transport of NAD is not a normal role of niacin transport at all. The transport of NAD through the blood does not happen. The transport of nicotinic acid, it happens when you megadose, when you get flushing responses, when you're trying to suppress your blood lipids, but that is not a normal transport mechanism for niacin. If you eat normal food amounts of niacin, the only thing you'll find in the blood is nicotinamide, unless you had a very high plant-based diet supplying a lot of nicotinic acid that you temporarily overwhelmed the liver's ability to convert it into nicotinamide.
So real quick, the only way that you will exceed this completely normal physiological response is, again, if you consume more than 40 milligrams of niacin within a single meal. Because, well, probably even more than that, because a meal...
40 milligrams of nicotinic acid.
Right. Because a meal is going to take, it's going to be even higher than that, because a meal is going to take hours to digest and absorb. You're not going to get all of that nicotinic acid at once as you would if you were to take a supplement. And so because that methylation pathway has a rate of 40 milligrams per hour, you would need to take, some dose of nicotinic acid in your meal from food that would be like 80 to 120 milligrams if it's going to be absorbed over 2 to 3 hours in order to start to expect to see anything other than niacinamide in your serum.
Yeah, so as we'll see when we get to foods, it's just completely impossible to consume an amount of nicotinic acid from foods that's going to saturate those pathways sufficiently to generate circulating nicotinic acid. So nicotinamide is the choice of transport to all tissues outside the liver. In addition to the nutritional niacin that's coming in, the liver will make some niacin from tryptophan, and the kidney will make some niacin from tryptophan. It's about 95% liver, 5% kidney. And so the kidney will make some of its own NAD from that, and will make some nicotinamide from that, some of which enters the circulation. But overwhelmingly, the liver is taking nutritional niacin, and it's taking endogenous synthesis from tryptophan, and it's releasing nicotinamide for transport to the other tissues. Now, what does that say for taking nicotinamide riboside? Well, Josh Rabinowitz's group published 2 papers, one in 2016, and one in 2018. Both of these will be linked to in the show notes. And these have been widely talked about because they're the very elegant tracer studies showing exactly where these things are going in the body. They're in mice, and so there might be differences between mice and humans, but right now this is the best information that we can possibly go on, and everything we know about this is extraordinarily similar between mice and humans. So what they showed was that if you take nicotinamide riboside, it gets absorbed intact into the liver, right? That means that you do not break apart the nicotinamide riboside in the intestine. It gets into the enterocyte, gets into the portal vein, gets into the liver. When it's in the liver, it's very good at generating NAD. A tiny bit of it passes directly into the blood. A tiny bit gets into the muscle and produces NAD. But the amount in the muscle, the amount that gets into the muscle and produces NAD is extremely trace. Overwhelmingly, what the nicotinamide riboside is doing is, yes, generating NAD in the liver, and yes, increasing the liver's NAD pool, but then the liver nourishes all the other tissues with nicotinamide, just like it does when you take any other supplement. But what's really fascinating is that in a very minor portion of their experiment, they didn't report anywhere near as much data for this part, they showed that if you just fed them nicotinamide, you did not get as good of an NAD response in the muscle. You got much better muscle response from nicotinamide riboside. Why would that be if the nicotinamide riboside is not getting to the muscle? If it's only making it to the liver and being converted to nicotinamide in the blood, why would it matter? Well, this goes back to the rationale that I was saying before. If you take nicotinamide, immediately the first thing that you can do with it is methylate it and get rid of it into the urine. If you take NR, then you cannot get rid of it until you first make NAD from it. And then you break it down to nicotinamide, and then it is exposed to methylation. So what I'm imagining is the NR is getting all the way to the liver, and then it's building up the liver's NAD supply far more than the liver would usually have. And because the liver has this big supply of NAD, it now has a lot more to work with to slowly release nicotinamide into the blood to get to the muscle. It's not overwhelmed with all this nicotinamide. What do I do with it right now? I can't release it to the muscle yet, so I got to flush it out, methylate it, get it into the urine. Right? So the nicotinamide doesn't produce the same results because it's so quickly sapped away into the methylation pathway that it just doesn't have as much of a chance to build up the liver's NAD reserves. And so will nicotinamide riboside increase NAD in your muscles? Will it increase NAD in your brain? Will it increase, I don't know. But my suspicion based on what they're showing in mice is yes, but not by getting those tissues intact, by being a much better contributor to the liver's NAD supply to allow a much better controlled release to nourish those tissues with nicotinamide. Interestingly, in the more recent experiment in 2018, they showed that if they used intravenous vitamins, that some of the tissues had some ability to take up nicotinamide riboside, nicotinamide mononucleotide, and use it, but the brain had no ability to do so. So only nicotinamide gets into the brain. But realistically, when they fed them the oral nutrients, it just doesn't matter if the muscle can take up nicotinamide riboside intact, because when you take nicotinamide riboside, you're overwhelmingly what you're doing is getting a better nicotinamide circulation response that's nourishing the muscle with the nicotinamide. And probably for the brain, you can only ever do that, even if you're injecting these nutrients. What else can we say about the physiology? Well, estrogen is a very strong regulator of the conversion of tryptophan to niacin. This is interesting on so many fronts. First of all, it suggests that women have different niacin needs than men do. In fact, if anything, it would seem to suggest that women have not higher niacin needs than men do. It also might mean that and I'll get to this later, that the production of niacin from tryptophan in women might be less variable and more regulated than it is in men. And there's some data to support that. It also might mean that the need for niacin goes up in pregnancy, because when do you see estrogen peaking? Well, you see it in events that are related to fertility in the menstrual cycle, and then in pregnancy you see it going up. So maybe this is designed to help eventually nourish the fetus with adequate niacin status, or to support the energy needs of the mother when she has the possibility of becoming pregnant, or when she does become pregnant. This also is the basis of why estrogen increases your needs for vitamin B6. So when people go on oral contraceptives, when women go on oral contraceptives, they have markers of vitamin B6 deficiency spilling out into their urine. And 2 episodes from now in this series, we'll talk about vitamin B6, so we can talk about that in more detail. But those markers are coming out of this pathway. That's a result of increasing the conversion of tryptophan, to niacin. I don't have too much to say about lactation, except that niacin is secreted into the milk to nourish the baby, and that comes with needing a little bit extra niacin to put into the milk, and a little bit extra niacin to nourish your energy metabolism for the energy that's used to produce that milk. So Alex, now that I've gone over like the basic 101 of the physiology, what can you tell us about the studies that you looked at in humans what do we know about the pharmacokinetics, meaning how these different forms of the vitamins are absorbed and transported from human studies?
Okay, so we do have a handful of human studies looking at nicotinamide riboside, NR, and one of the best ones was done by an independent group of researchers that weren't actually creating a supplement and selling it, which is who has sponsored and run most of the other trials. And in this study, they had a small group of 8 healthy adults, 6 females and 2 males, supplement with a supplement called Niagen. And they self-administered these caps on days 1 and 2, they took 250 milligrams. On days 3 and 4, the participants took 250 milligrams twice daily for 500 milligrams per day. Then they took on days 5 and 6, 500 milligrams twice daily for 1,000 milligrams per day. And then on days 7 and 8, they took 1,000 milligrams twice daily for a total daily dose of 2,000 milligrams. And on day 9, they gave all the participants 1,000 milligrams and then monitored all of their blood stuff for 24 hours after that to see what happens. And what they found first and foremost is that there's huge individual variations in the response with nicotinamide riboside supplementation. So, for example, even after supplementing up to 2 grams per day, there was actually one participant who showed a 10% decline in serum levels, whereas everyone else increased, with some people showing increases up to 120%. And in the actual pharmacokinetic study, following an acute dose of 1,000 milligrams, the peak occurred at around 3 hours after ingestion, but that was only in 4 of the 8 participants. The other 4 didn't show any peak at all. Their blood levels didn't change to supplementing that 1,000 milligrams. Now, that's looking at blood levels of NR. When you actually look at levels of NAD, you're also going to see huge variation, but more consistency in how people respond to NR supplementation. So, like at baseline, people ranged 1.8-fold in how much NAD they had in their blood before they even started the intervention. And the increases in NAD from supplementation over this 9-day period ranged from 1.3 to 2.7-fold. And when they did the pharmacokinetics study, they found that NAD didn't increase from the baseline of after. So they gave them 1,000 milligrams, but NAD didn't further increase over the following 24-hour periods because their NAD levels were already what the researchers believed to be capped out from taking the 2,000 milligrams for the 2 days prior and the 1,000 milligrams for 2 days before that. So there's a saturation effect with the NAD where you're not going to see further increase above what you could get with 1 to 2 grams taken per day. And there were no adverse effects or side effects due to any of this, except, interestingly enough, there was a significant decline in serum potassium levels that I don't have an explanation for. The normal range is like 3.5 to 4.3 or 4.5, and their levels declined from 4.1 to 3.7. And there were also minor but significant declines in hematocrit, hemoglobin, and platelet counts. I don't have an explanation for any of this, but they are side effects that could become more pronounced in susceptible individuals.
Did they measure the blood levels of nicotinamide in this paper?
No, they didn't measure blood levels of nicotinamide, but they did measure blood levels of nicotinamide mononucleotide, and that didn't show any change in response.
Yeah, so I mean, it's my suspicion based on everything I've read about the physiology that there was probably a very big increase in nicotinamide, and that was probably what was mediating like most of the NAD that reached any other tissues.
Yeah, so when you were talking about degradation, one of the things that I think gets overlooked a lot simply because it's not well investigated is going to be the microbiome. So I think that it's plausible that, people have different microbiomes with different diversities of bacteria that have different functions, right? And so it's I would speculate that it is possible that some people have more bacteria that possess the nucleoside phosphorylases that would break down the nicotinamide ribose into nicotinamide before it's absorbed into circulation.
Right, but so maybe if someone has SIBO and they're producing those enzymes, then sure. But based on the physiology of the transport between different tissues that we know so far, the nicotinamide riboside, assuming it does get intact, is going to the liver. It's being broken down in the liver to nicotinamide, and it's overwhelmingly being nicotinamide that's released into the blood. So, maybe there's some people who have more intestinal bacteria in their small, because remember, this also is absorbed. You're at least you're starting to absorb it quite rapidly in the upper small intestine, right? So, so people with SIBO of a certain type, maybe they're degrading this to nicotinamide before they absorb it, but the people who don't are degrading it to nicotinamide in the liver, not to break it down, but because it is the physiological transport mechanism of the body to circulate niacin as nicotinamide. Like that is the circulating form of niacin. So it's like what you would if you're trying to reconcile this study that you're describing with the mouse study that I was describing, like you would expect nicotinamide riboside to enter the blood at a certain amount, but if you look at those mouse studies and you compare the absolute amount of nicotinamide riboside in the blood to the nicotinamide response, overwhelmingly it's nicotinamide in the blood that's being produced by the liver. And in the mice studies, they have tracers that show, like you just watch the tracer go into the liver to generate NAD, then to generate NAM, nicotinamide in the liver, right? So, it's interesting that they didn't look at nicotinamide. That would have been like one of the top things that I would have wanted to measure. I wouldn't have cared to measure NMN in that study.
Yeah, okay, that makes sense. The takeaway being that in humans, at least in healthy humans, we have no idea how someone's health status would affect any of this. But in healthy humans, nicotinamide riboside is going to be absorbed, and it is going to increase blood levels of NAD. In contrast to that, nicotinamide mononucleotide, we have absolutely no human studies that I'm aware of looking at how supplementation does anything. Like they don't exist, at least not yet.
All right, this rounds out our understanding of what niacin is and what it does. In 2 weeks, we will see the practical side of niacin when we look at blood tests, food, and supplements. This episode is brought to you by Ample. Ample is incredible. It's a meal in a bottle that takes a total of 2 minutes to prepare, consume, and clean up. 2 minutes. I'm not kidding. Now, I know what you're thinking. Anything that quick just has to be made of synthetic ingredients that you'd have a hard time pronouncing and wouldn't want to put into your body. But it's not. Ample is made entirely from natural ingredients and designed to provide an optimal balance between protein, fat, and carbs, as well as all the vitamins and minerals that you'd need in a single meal. There's no question that it's always best to sit down and take your time eating a home-cooked meal from fresh ingredients. But let's face it, oftentimes we just don't have time for that. If you live a busy life like I do and your goal is to get things done, you need quality fuel that you can get into your system quickly. Here's a great example where Ample is perfect for me. When I shoot videos, it takes hours to set up and break down all of my equipment. So I try to get as many videos shot in a day as possible. This prevents wasting a lot of time on setup and helps me conserve big blocks of time outside of shooting videos to get into a flow state where I can research something to my heart's content and spend all the time I need thinking about it creatively and analytically. But if I spend hours dealing with recording equipment plus hours spent preparing food, eating it, and cleaning up, there's no time left over to actually shoot any videos. So on recording days, I use Ample to maximize efficiency and focus on getting things done. Ample comes in 3 versions: original, keto, and vegan. And each version comes in 2 portion sizes, 400 calorie and 600 calorie. The 600 calorie original version gives me 37 grams of protein from a mix of grass-fed whey and collagen, which promotes satiety and flips my brain on. Its fat comes from coconut oil and macadamia nut oil.
I like these oils because they're low in polyunsaturated fatty acids, or PUFAs, oils that promote aging and are usually loaded into the processed foods that most people eat when they need something on the go. The coconut oil provides some medium-chain fats to keep my energy levels up, too. The carbs, the vitamins, and the minerals all come exclusively from food sources like sweet potatoes, bananas, cocoa powder, wheat and barley grass, and chlorella. It's full of natural prebiotic fibers and probiotics to promote a healthy microbiome, and the gentle sweetness comes from a mix of honey, monk fruit, and stevia. I just mix it with water, drink it, rinse out the bottle, and boom, 2 minutes in, and I'm fully fueled and ready to face the next phase of the day. I first came across Ample when I met its founder and CEO, Connor Young, at PaleoFX a few years ago. Connor inspired me with his vision for Ample, which I anticipate will be much more than a meal in a bottle in the near future. I've become an official advisor to Ample, and I'll be helping Ample design scientific research that will lead both to an ever-improving Ample and, I hope, meaningful contributions to our understanding of how to use nutrition to help people be healthier and happier and perform better at the challenges that they care most about. As a listener to the Mastering Nutrition podcast, I've also worked out a special deal for you. If you use the discount code CHRIS15, you'll get 15% off your first order of Ample. To get your discount, go to amplemeal.com. That's amplemeal.com, 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 and use the code CHRIS15 at checkout. This episode is brought to you by Ancestral Supplements. Traditional peoples, Native Americans, and early ancestral healers believed that eating the organs from a healthy animal would strengthen and support the health of the corresponding organ of the individual. For example, the traditional way of treating a person with a weak heart was to feed the person the heart of a healthy animal. Modern science makes sense of this. Heart is uniquely rich in coenzyme Q10, which supports heart health. The importance of eating organs, though, is much broader than simply matching the organ you eat to the organ you want to nourish. For example, natives of the Arctic had very limited access to plant foods and got their vitamin C from adrenal glands. And vitamin C is important to far more parts of your body than simply your adrenals. In his epic work, Nutrition and Physical Degeneration, Weston Price recorded a story of natives who cured blindness using eyeballs, which are very rich in vitamin A. But now that we understand vitamin A, we know that we can get even more vitamin A by eating liver, making liver good for your eyes. Our ancestors made liberal use of organ meats both to be economical and to utilize their healing and nourishing properties. Animals in the wild do the same. Weston Price had also recorded a story of how the zoos in his era were capturing lions, tigers, and leopards, oh my, only to watch them become infertile in captivity. Researchers then observed what the lions did when they killed zebras in the wild. What they did was they went straight for the organs and bone marrow, leaving the muscle meat behind for the birds. But even the birds took what they could of the organs and bone marrow. Price reported that once the zookeepers started feeding the animals organ meats, boom, their fertility returned. The problem I often encounter, though, is that many people just don't like eating organ meats. Let's face it, if you weren't raised on them, it can be very hard to acquire a taste for them. That is where Ancestral comes in. Ancestral Supplements has a nose-to-tail product line of grass-fed liver, organ meats, living collagen, bone marrow, and more, all in the convenience of a gelatin capsule. For more information or to buy any of their products, go to ancestralsupplements.com. Ancestral Supplements, putting back in what the modern world has left out.
All right, everyone. Thank you so much for listening. I hope you enjoyed part 1 of niacin. Part 2 will be published in 2 weeks. Part 2 will cover the practical side of niacin. It will cover what to do to manage niacin nutritional status, both from the perspective of blood tests and what you should be eating in order to get enough niacin. And it'll talk about niacin supplements, what form you should take, how should you take them, what should you take them with, how do you manage the side effects, and what can you expect, if anything, for positive health outcomes. If you want more of me, you can find me at chrismasterjohnphd.com. If you want more of Alex, you can find him at alexleaf.com. If you want both parts of the niacin series right now, you can sign up for the CMJ Masterpass at chrismasterjohnphd.com/masterpass/mastering nutrition. Using that exact URL or clicking the link in the description of this episode will give you a lifetime discount of 10% off. In the CMJ Masterpass, you not only get early access to Mastering Nutrition, you get transcripts and you get ad-free content. And you don't just get this for Mastering Nutrition, you also get it for Chris Master John Light, my 5 to 10 or 2 to 10 minute short practical tips. And as soon as I have the Mastering Nutrition series on a regular once-a-week schedule and I'm a little bit ahead of the game, I'm going to get right back to Masterclass with Master John for all those detailed biochemistry classes with slides and videos that some of you love so dearly. On top of that, you get access to once a month and sometimes more Ask Me Anything sessions over Zoom, where you can ask me anything. You can ask me anonymously. You can share your name. You can ask by text, or you can even come on the screen and use your webcam, share your screen, do whatever to ask your question, and all have a fun educational time together. You only need to love one of these things for it to be worth it, so consider signing up for the Masterpass today. Hope you enjoyed the show, and I'll see you next time.